So today we're going to have the block diagram reduction. First, what's block diagram? Block diagram, it's a method, a graphical method to represent the relationship between the input signal, so that will be the input signal, and the output signal, and what you have inside transfer function. Okay, so that's a block diagram for one function, for one device, for one system. But usually a complete system consists of many blocks, and maybe the way that they are connected or interconnected a little bit complicated or very complicated. And in the end, we need to reduce and simplify the all blocks to have only one block, that it reduces the system to one block, and it shows you the relationship between the input and out. For example, you can find something like that, and we're going to solve it in the end of the class. You may find some kind of block diagram look like that. You have summing point, and then you have block, let's call it G1. You have another summing point, another summing point, and this is the input to the system, and you have another transfer function G2, and this is your output CS, and we have something here called H2 coming from the output C, and maybe you have something here going to H1, and another one coming from C. And if you put the sign, this is positive, this is negative, and this is positive, positive, and here positive, negative. Do you see? This is block diagram for the whole system when we look at it. And of course, I mean, it's very hard to find the relationship between the output and the input. So we have to find a way to reduce all these block diagrams only to one block like this one. So now can you imagine, I mean, the problem, right? Yeah. So we want to find rules how to reduce this one. So let's take, I mean, simple rules, and we understand how these rules work out, and then we'll try to solve this example. Because, I mean, in this example that I give it to you, you just need to reduce everything to one block only, and you have only R of S as input signal, C of S as output signal, and you want to find what's inside this block. This is, I mean, the objective of today's lecture. So let's check some rules here. The first rule that we are going to do is very simple one. When you have block diagram cascade, in cascade means series. If you have if you have something like that, and this is called G1, and you have another one G2, and this is the input of the R of S and the output C of S. So you can reduce these two blocks in cascade, call it cascade or series, right? There are two words for it. So how you reduce this one? Do you have idea? If you want to make one block, what you write inside?
Summation.
No, G1 times G2, not summation, multiplication. You know why? No, it's very simple. Let me show you the first one. Let us R, the input and the output called here X of S. So what is X of S? Is equal the transfer function times the input, right? It will be G1 times R. Okay, what's C? The output is equal G2 times X. G2 times X. What's X? G1 R. So what is C? Is equal G1, G2, G1 R. That's, I mean, the way that you can find out the equivalent block diagram. So always don't guess, just work it out. Okay, you understand this one? And let's now get the combining blocks diagram in parallel. Now I'll go in parallel. What look like? You have, for example, G1 of S, and you have G2 of S. And the input R of S is common to both blocks. Means the input for G1 is the same for G2. And the output of both, you just sum or subtract, whatever. Let's say that both of you are adding. And this is your C of S. I want to represent that by only one block. Has the input R of S and the output C of S. Let's work it out. How we do it? You'll say, okay, this R input and R input, let's say that you R times G1, you get X1. R times G2, you get X2. So what's C? The sum of X1 plus X2, right? What's X1? G1 times R, right? G1 times R. Plus, what's X2? G2 times R. So take R as a common factor. So what you got? G1 plus G2 times R. So what you put inside there? G1 plus G2. G1 plus G2. Maybe somebody say, okay, what about if you have this one negative? You will have here negative. So you have G1 plus G2 or G1 minus G2. It depends on the sign of G2. So what do you call this block diagram? We call it, in parallel. Yeah, this is in series, this is in parallel. So let's write, that's in parallel. Block diagram in parallel. And the other one you see is okay. Let's now look for something else. Now I'll show you something very important that it's called, feedback loop. Feedback loop. And usually the student confused between feedback loop and in parallel because they look very similar. What's look like? You have G as the transfer function and summing point, and the input is R of S, the output C of S, and then you have the negative feedback H of S, because it's negative feedback, so here will be negative. What do you observe? We observe here that the flow of the data or information in this direction, right? And then after the output, then the flow of the data going in this direction. That's why we're calling them feedback. But when you look for the in parallel, you'll find the flow of the data in this direction and the flow of the data in this direction, and you add or subtract. So that's the difference that when you look at it. How you reduce this one only to one block? We want to have only one block. The input is R of S and the output is C of S. Let's just look at it. For simplicity, we are going to call this signal E of S. And usually you call E of S the error signal, right? It's the difference between the reference and the output of the sensor. So what is C? But before we forget what we call this, we call it feedback loop, Call this feedback loop. So, what's C? If you look at C, C is here, right? And here also. I'm talking about the C output here. Is equal transfer function G times E, right? So I would say it's equal G of S times E of S. Now, what is E? E is the output of the summing point, right? E is equal what? R of S minus this value, right? Call this B of S, okay? So is equal E of S minus, E is equal R of S, right? Minus B of S. Great. Now, G of S, R of S is R of S. What's B of S? It's an output, right? How you get B? C of S, right? Times H, right? So let's say H of S times C of S. Okay. Now let's say C is equal G times R, right? Minus G times H times C. Now we have C, you have C. True? Take this one on this side. So what you have? C plus GHC equal GR. True? Take C as a common factor. So what you have? 1 plus GH equal GR. Now you want to find the output over the input. What's output over the input? C over R, right? So what's C over R? Divide by R both sides. You will have R left, you will have G left here, right? You will have G over 1 plus GH. That's the answer. So C over R will be equal G over 1 plus GH. So when you have feedback loop like that, you have G going in the forward, and the feedback, you have H, and you have negative. So you have 1 plus GH and G over 1 plus GH. If you have positive feedback, so this will be negative. So it's like the opposite, right? So what's the reduction of the all feedback loop here for negative feedback? It's equal G over 1 plus GH. That's the all reduction of this one. That's a very important rule, because most of the control system has feedback loop all the time. Okay, that's a very important one. Let's take another thing.
Doctor,
yeah.
Positive feedback. What did you say about?
Pardon me?
The positive feedback.
The positive feedback, instead of the negative here, you have positive. So you will just change the sign. Instead of 1 plus GH, it will be 1 minus GH. Yeah, it will be the same. Just flip the sign. Now we'll get another important thing. It's called moving a takeoff point. Moving a takeoff point beyond a block. These, I'm going to give you 2 rules, are really very helpful in solving some problem. Let's say that you have signal here called, for example, R of S going to some block called G of S, and you got the output here C of S, and you have some takeoff point here going to another place. All right. So of course this one will be R of S also, right? Because no change, just it's going here, and you make branching, so takeoff point. We call it takeoff point. Sometimes you need to move this point from here beyond the block. You want to move the point here. So what change you will do? It means you want to move this point here. You want to make it here like that. So it will be like that. What I mean if you move it, you will leave this. If somebody think about it, say, okay, that's G of S here, and I move this point here, so the point will be like that. That's not true. Why? Because this is R of S multiplied by G of S, got C of S. This is right. But this one is not R of S. It was R of S. Now it's equal G of S times R. It's not as before. So what should you do to get it back as R? Divided by G. That's true. So we'll just write 1 over G. You got it the same thing. So if you have a point, we call it takeoff point, and you want to move it beyond the block, this one going forward is going to change? No. Because you multiply R times G got the C, the same thing. But the problem with the other branch that coming before that, you got to divide it by A, by G. So always put this in our mind one more. And you don't have to remember, just every time making some kind of any transformation, just check back that you're getting the same value of the signal. Okay. Let me give you the last one. There are many things, but the last one, the basic. What about if you want to move the takeoff point ahead of a block? The opposite. Moving a take off point ahead of a block. Well, this will be something like that. You have here input R of S going to a block G of S. You got C of S, and then you have the branching here, the takeoff point from here. So what's the output here? C, right? Which is equal G times R. Okay. What about if you want to move this point where? Back. So let's sketch it. I will have here, I will sketch it as it is. This is G. I got here C, and this is the move here. This is R times G is equal C. C is equal G R. That's fine. But this one is R. It was not R. It was so multiplied by G. That's it. So we are done with the basic rules that you should be capable to solve anything. Now we'll go to our nice example in the beginning, and we'll try to apply these rules together. Okay?
Can you explain the last bit?
The last one you have here R multiplied by G. You got C, which is equal GR. The branching is here. The takeoff point is here. It was equal to C, GR, right? If you move this point here, this is R, so this will be R. But you need to get GR, so you multiply it by G to get GR as before. So the trick is every time you are going to move any point beyond or ahead, you have to keep the signals as before. That's the only thing. No change should happen. I will make now copy of this problem, and we'll see how can we apply the rules we just learned to reduce it. Very interesting problem. And I advise you to solve as much as you can to get experience. Did you see using algebra or calculus? Nothing, right? It's just playing around like a puzzle. So let's see how clever you are. All right. Here you go. This is our system. So I want to ask you what you are going to do.
We start from there. From where to start?
We'll start. Okay, this is good. When you look at it, you know some rules that you know. You know parallel, yeah, you know feedback loop. These are the two basic. Okay. You have something easy, like if you are parallel or series for feedback. So you look for these three things, and if you find it, do it. If you found it's hard to do it for some problem, solve the problem. And usually the problem that you are moving the point. So for example, here, it will be nice if you don't have this patch.
Yes.
Right? So you'll be happy if you can move this away. Right? So that's what I'm saying. You look for the rules that we learned just now, and see if you want to apply. If it's easy, apply it. For example, for this block, you'll observe that this is kind of feedback, right? It's kind of feedback. But the problem that there is something coming here. So this is like annoying. True? This is one. So you may start with it. This point is annoying because if it was like that, for example, if this is H2 and this is G2, I'm assuming, and it looked like that. and nothing here. Nothing, يعني this one is not a there. And I ask you to reduce it. You will say that, and this is, I mean, positive, and this is negative. When you look at this one, it look like parallel or feedback? Feedback. Why? Because the information this way? Mm. So how you'll do it? You will say, okay, I will do it, this is in the forward, and this is in the backward, so be equal, and this is negative feedback, so it'll be equal G2 over 1 plus G2 H2. You told me, but it didn't look like that. Okay, you can flip it. You can say it's G2 H2. All right? And you have the summing point. The positive is going in this G. And then the back to H, and H going to the negative. So it's the same. Just, I mean, flip, mirror. So this is nice. But can you do that here? No, you can't. Why you can't? Because you got the point here, take off point. Now the very important question. Are you going to move this point here or there? To the right or to the left? Why don't move it to the left? No, not anything. This point, any point, do not move it beyond or ahead of summing point. Don't move it here behind summing point. Why? Because this point coming after adding to signal, not multiplying or dividing. So how can you take this one and put it there? This one is the result of G1 times this one plus G. So how you get it there? You are going to lose this one. But here, you can move it there. Why? Because, I mean, this one, if we call it X, all right? If you move it there, it will be X times G2 and divided by G2, you get rid of it. All right? So let me get this part. Let me cut this part. I'll just take this part. Copy. And let's see what you'll do. Here, that's the problem exactly that I have. So I want to move this branch there, but I have to remember here is X. Here is X. If you have here X and you want to move it, you got to keep it X. If you move it, let me make just, I mean, broken line. If you move it there, what is the signal here? Is X? No, X times G2 is a G2X. G2X. You got to get it X back. So what you'll do? Divided by G2. So all what you're supposed to do, you get there, and then you say 1 over G2. And you move it there. And you erase this one. And when you do that, you are fine. Now you can do your feedback that we just did. Before that, you can do it, right? So now, G2, H2 already reduced it, so we'll have G2 over 1 plus G2, H2. This is the block, represent what? Represent the whole thing here, right? And then you got here C, and then you got here what? 1 over G2. And then what you have here? H1. You can continue, you continue to finish A. Now, here what we did. So let's take this one and just we sketch the what we did. All right. Just I was explaining, it's just partial here. Now I will just put it there next to it, so we'll understand what we did. So what you are going to erase from this one? This point, right? You are going to erase this one. All right. And you are going to connect with what? 1 over G2, true? And this one coming from where? From C, the same thing here. And this one block, I'm going to remove it, true? And I will have the equivalent. What's the equivalent? Exactly, G2 over 1 plus G2, H2. Now, this is our new graph. Very easy thing I'm going to do. This block and this block, they are in series. I just multiply. So I would say it's equal, let's make it blue now. It's equal G1 times G1 times G2 over 1 plus G2H2. All right. And you have a block that's C, that's the summing point, plus R. And this one you had positive. And here you have also another A series. So you got H1 over G2 coming from where? From C. Because all this C, right? And then you have the last one. I'd like to sketch like that. I know it's coming from, but it's the same, right? It's the same. So I would say there's another one coming there and going to the negative here. Can you now finish it? Yes. What about this one in the middle? Another feedback, right? Well, so how we do it? But you know, when it looks complicated like that, you can call it any name. Like, say, call it G and call it A, H. So what do you have? G over 1? No, minus GH. Because you have what? Positive feedback. Be careful. So, this is, you can abbreviate. I will tell you about something that makes it simple. Usually when you have fraction like that, usually I call it like a G is equal A over B and H C over D. All right? And now I want to find G over 1 minus GH, right?
Yes.
G is equal A over B, all right, A over B, over 1 minus G A over B, H C over D. And then simplify it just before you put all the things, because sometimes you have very, big function. Now I multiply it by BD, the top and the bottom. Why? The common denominator. Yeah. So I multiplied here the whole thing by BD. I multiplied all this by A, BD. So what I get? BD times A over BB cancel with B. So it is left AD over BD times 1 minus BD cancel AC. So this is your A. Fine. Now I can write just easy. What is A? G1, G2. G1, G2. What's D? G2. Right? So it's square. Over. BD. B is equal this things, right? 1 plus G2, H2. Times D. G2. I put G2 here in the minus A. G1, G2. C. H1. Okay. You're done. You're done with what? With this part. So I'll put this block. Sometimes, it will look messy. Call this one all A. G3. The whole thing here called A. So I'm going to remove all this block and I put G3. So you have here G3 block, and then you got summing point R, C, and then you got A, just one. Another feedback. But what's H? There is no H here. Is it 0?
It's 1.
It is 1. Why? Because no change. C is C. So if you wish, you can make it like this one. If you write 1 here, nothing, no change, right? C is C. So now we have G3 over 1 plus G3H. So just the 3. And you have G3, you can just simplify. This you have G3, you can call it A over B, and you do the same business with it. But here, khalas, you are done. It will be in the end 1 block equal G3 over 1 G3. You have C. You reduce the whole thing to 1 block. So did you understand the idea?
Yes.
Do you have any algebra? No. Do you have any